Hi, in this video I'm going to look deeper into the question of looping in Collatz type conjectures. This is one in a series of videos I'm making about the Collatz conjecture, the 3x plus 1 problem, in which I suggest the problem is far simpler than assumed by mathematicians. So what we're looking at here is an input-output table that describes in odd numbers only any Collatz sequence. Obviously the table can be extended much further down. Let's look at any number, say 49. It goes to 37. 37 goes to 9. 9 goes to 7, 7 goes to 11, 11 goes to 17, 17 goes to 13, 13 goes to 3, 3 goes to 5, and 5 goes to 1. Now that is a Collatz sequence without the even numbers, and you can check it out for yourself. What I want to illustrate is something very, very important, and that is this difference between 1 and 11 in relation to 5 and 7. So 5 to 1 is minus 4. 7 to 11 is plus 4, and this is a inverse relationship, and that is of great significance because the terminating loop for Collatz conjectures is 5, 1. You do have another minus 4 that is isolated, it's on its own, and it has no consequence in producing a loop. So you can think of 1 as being in a loop. It's called a trivial loop. So it's looping 1, 4 to 1 in the even sequence. In the odd even sequence, in the odd sequence, it's just 1, 1, 1, 1, 1, 1, 1, 1. It's just at light speed spinning around itself. It has a zero difference. Now, let's compare this to a completely different input-output situation where it's 3x plus 17, and we see two inverse relationships on either side of 0, which 0 is the termination of the sequence because it's a loop. 17 to 17 is the end of the loop. Input 17, output 17. So just like for the 3x plus 1 problem where input is 1 and output is 1, for the 3x plus 17 operation, it's input 17, output 17. Now, by and of itself, that explains the 3x plus 1 result that always ends in 1. That is such a strong heuristic right there that should satisfy logical minds. However, it's probably not enough for mathematicians because it doesn't discount the possibility that there could be some kind of loop far, far down this table. No matter how fantastically abstract and unbelievable that possibility is, but if you can see the growth in the differences, it certainly does seem impossible going down and seeing these differences between back-to-back operations. That's really what I have to say about this feature or this property. Notice that the inverse pairs are symmetrical where n